as I said, we are going to talk about causal data science and how we use it in retail in Marks and Spencer. Just a few words about Marks and Spencer. It's a business which is both online and also brick and mortar shops. We have around 30 million known customers, a loyalty card called the Sparks, 15 million users for that. Around the world, we have 1,500 stores, and it's a business of 11 billion in terms of revenue. So why basically we like causal inferences? Because of the influence that it's had in some of our use cases. So we use causal inference in offer, which is the use case that we are going to talk about today, and also we use it in our forecasting work and time series, using of various time series within Marks and Spencer. So for example, in this use case, we had increase of 100 million pound in just one of our use cases. This is why we like it, basically. But talking about today, we are going to talk a little bit about causal inference and basically how we quantify that. We want to put a number for effect of one thing on another. And then the framework that we use, commonly known as average treatment effect, we're going to talk a little bit about it, and then the so-called fundamental problem of causal inference. Now, we hear this thing, people say correlation doesn't imply causation, but what does? So we try to answer that question very briefly as well. This is about machine learning and meta learners and how they are used for computing average treatment effect. So we're going to talk a little bit about two meta learners. And then after that, we look at how we use all the above in a use case related to loyalty program at the Spark. We talk a little bit about engineering challenges, and then we wrap up. So let's start. So generally, when we talk about causal inference, we talk about inferring effect of one thing from another. So for example, taking a tablet and say an aspirin and recovery from that because you had headache. But always there is this what if question, that what if I didn't take that tablet and I still recovered, right? So it is about this sort of scenarios, things which may not happen. Similar to that, receiving an offer. So if we give a coupon to somebody, how much that would affect in purchasing of items that that person wants to buy. The other example is attending private school. So there is this debate, always all families think about it. If I put in my kids into private school, am I going to have better result and higher average mark? But is it because of private school, or is it because of the setting of the family that you have? Anyway, they would have had higher marks because you work with them at home or other compounders related to that. So these are the type of questions that we typically answer. The terminology is a little bit like geared towards medicine and drug trials and all that. So you hear two things, treatment and outcome. So treatment, all those blue items that are highlighted in blue, they are like treatment. So and the outcome, what follows is all those magenta and pink at the other side. And if you want to mathematically model them, they are really random variables that they take two values. So taking the tablet or not taking the tablet is 0 and 1. And 0 is typically when the tablet is not taken. We call that control. And then the other one, we call that treatment. Similarly for outcomes, so that is also a random variable. Now, when I say random variable here, they are discrete. They can be non-discrete as well, as you will see in a bit. Okay, that's good. That's good. So if causal inference is about inferring the effect of one thing on another, we are data scientists, we talk about numbers, right? So we are always after quantifying the effect of some causation, right? So how do we do that? Typically, mathematicians like to have single number, mean, median, all that. Why? Because single numbers are good for comparing things, saying this is better than that. Sending to a school, private school, not sending, right? And the way that this is done typically in causal inference is using mathematical expectation. So I've written the formula for mathematical expectation in the first block. It's really weighted average. You take the values of X, you look at the probability for random variable equal to that value, and then you calculate the weighted average. So if you are not familiar with expectation, just think of it as best value. So say for the sake of argument, consider a dice, 6 values, and imagine you have 1/6 the probability of when we throw a dice. If you calculate expectation, it works out 3.5, right? It's basically saying that if you try throwing a dice over a long enough period of time, roughly that best value is 3.5. So that's good. Now, we talk about taking pill or not taking a pill. Outcome subject to some conditions. So those typically we can calculate with conditional expected value. As you can see, the final equation there. So we can calculate it like that as well. So this is very good, because if we have all these expected values, then we can look at different scenarios and kind of compare them against each other and make a decision or sort things out. So this is very valuable. Now, we need one other piece of notation, and that is the concept of causal effect. So it turns out that in order to properly do causal effect, we need something called do calculus, and we are not going to go into it, but it is an elegant mathematical formulation for describing causation. So for example, if you look at that block, outcome with treatment, it has an operator called do. And what happens is that, what do we say? Taking a tablet and the results. So there is an element of do. So intuitively, it kind of makes sense. But Pearl in his book, in his various books, so for example, the book of why, makes a discussion, it makes a debate that you need to have this do operation on top of classical conditional probability in order to do this elegantly and properly. So that's what they say. Okay, if you forget about this theoretical thing, so there is a notation here I want to introduce. So outcome of the treatment, so y subject to do t equal 1, as you can see in the first line in the white box, we abbreviate it as yi1. So this is a number. Similarly, for outcome without treatment, we represent it at yi0. So yi1 is outcome, a numerical value in terms of having the treatment, and yi0 is the outcome when we don't have the treatment. So the effect, the causal effect, is modeled as subtraction of these two. Very good. So you're probably going to say to me that, Behzad, now we have this value, we just need to calculate the expectation of it, best value for that. Now, this cannot happen for the reason that it's commonly known as fundamental problem of causal inference. And if you think about it, one of these two scenarios can only happen. So if you look at the tablet, taking of the tablet, either we take the tablet, each user, Behzad, if he has a headache, he takes the tablet, or he doesn't take the tablet, right? Unless if you have a time machine to go back in time and change it. So it's not possible to calculate this value, which is at the basically causal effect, yi1 minus yi0. As a result, we just don't look at one item. We look at a cohort, a few items, and we use expectation for a group of samples, right? And this is the concept of potential outcome. And this is the concept of average treatment, which was suggested by Robin. So we calculate expectation of y1 minus y0. Really, this talk is about how we calculate this and how we use machine learning to calculate that. But before we go there, let's dig a little bit deeper and try to answer in a way a question that probably is of interest to a few people. So if you look here in this definition of expectation, you see there is a sigma, there is a sum, the first box, and we can open that sum basically. So we can write expectation of y1 minus y0 as subtraction of two expectations, right? Very much related to that is this formula that I put it in a pink magenta box. So if you read that carefully, so it says expectation of y1, outcome of 1 in case of treatment, minus expectation of 0 without treatment. So if you look at this, this is very much similar to correlation, you know, how two things are correlated to each other. So it turned out that if these two values are equal, then the correlation is the same as causation. But these two numbers, the number in blue and the number in magenta, most of the cases, they are not equal. And hence correlation doesn't imply causation. And the reason for that is confounding factors like weather. So for example, if you look at that graph, weather, imagine you're selling skirts. So weather affects how much you sell the skirt. Also, weather affects how we do our offers, right? So this is a confounding effect. So in effect, that blue number and that magenta number, which are two numbers, if we want to add something or subtract something that these two values become equal, that would be the effect which is coming from these confounding of factors. And you have many of those. Weather can be one of them. It could be because of, if you're looking at this single store, it could be if there is any road work there. It could be combination of items. So for example, bacon and egg, how much bacon people buy, that relates and maybe influences how much egg people are buying, that sort of thing. So these confounding effects kind of is the reason that correlation is not equal to causation. And basically we can say that the reason that they are not equal is because of influence of those factors. Closely related to this is randomized controlled trial. So this is a way to randomize how these treatment and tests are picked up. So that is one of the cases that basically causation and correlation, they are equal, and you have equality in that formula both. But as we all know, and we've seen it in case of COVID, very close to what happened at home a couple of years back, RCT is not always possible. It's very expensive. Sometimes it's not ethically in some use cases possible. And we can't perform RCT in retail in Marks and Spencer. So how we are going to do that, how we are going to be able to calculate these expectations so that we can make good decisions. So I pass it to Dipankar, my colleague.
So as Behzad introduced before, that we can somehow use, we are able to remove the effects of confounders using randomized control trials, but randomized control trials can be expensive. For example, if you're a bank and you want to test out different types of loans, you cannot go around and start distributing loans to everyone because that is a very expensive proposition. So you want a more controlled way of understanding how your treatment might affect the individual units. So one of the ways what we can do actually is we can use machine learning predictions to actually understand the treatment from the existing data itself. So just putting it out there, I'm a big time foodie, so I'm going to use an example from food to actually help you understand how it can be done. So I live in Southall, which is like which is a good place to get Indian food. So, and one of my favorite food is actually samosa. So so basically there's a very excellent samosa stall in Southall, which where I'm quite a regular visitor. So, and what I want to understand is that how can sales of that stall can be predicted, can we relate it to the price of the samosas? Suppose if there is a change in the price, how it will affect. So what we want to build is basically build a model which will allow us to which will take in all the features like the price, what is the weather, whether the customer drinks tea, and if the customer is a repeat customer. And we'll try to predict the sales from this data. So once you have this, we would like to understand the effect of the treatment, which in this case is price on the sales. So what we can do is, so Behzad mentioned before, like the series of what if conditions here. So we can employ the same here. So we want to understand a few questions here, for example. So what if it is a rainy day? How does it affect sales? What if the customer drinks tea regularly, and how does that affect sales as well? So we are moving away from the previous treatment where we are talking more about the average treatment effect, which was being done over the entire set of data. And we are moving to and we are going more and more, we are looking into more specific sets of the data where we are looking at a few particular features, understanding how they can actually affect our sales. So this is where the concept of meta learners come about, because we are no longer looking into the average treatment effect, and we are going into the realm of what is known as the conditional average treatment effect. So what does this mean? So remember in the previous slide where we were talking about if it's a rainy day. Now that's a very specific feature of the data. So you can look at those particular data set where it was actually raining, and then you can compute the average treatment effect, but only conditioned on that particular data set. And basically, you can go ahead and actually compute this even for a single unit as well. So you can compute the conditional average treatment effect for a single unit. And this is and this can also be done for continuous variables. For example, price is definitely price is a treatment which is continuous in nature. Also, you have, for example, doses of medicine. So you might give them some different doses of medicine and then try to find out what is the effect. So you can also measure continuous, even if your treatment is continuous in nature, you can also use the rate of change of the output conditioned on the given single unit. So you can also compute the average treatment effect in that in such a scenario as well. So let's go back to the previous case where we are talking about the samosa stall. So we have the price, which is our treatment. And what we want to actually measure is this rate of change, which I was talking about here. So because this is a continuous treatment, you can actually compute the derivative instead. So what we want to compute is the rate of change of this, the output, which is the sales, with respect to the treatment. And this is just basically how a derivative looks like. So no surprises there. And this term is what is known as price elasticity. So what we have done here, we have taken a standard machine learning model. It can be a suitable model. And we have actually used the output of the model to predict another parameter. So basically we're not using the predictions in a direct way. We are doing some transformation on top of it and then creating this term. This is an example of a meta learner. So we have there are several types of meta learners, and this is one of the most simplest one. The one which I just showed above, this one is basically what is known as an S learner or a single learner, because you have just one learner here. So the S learner, basically what it includes is you basically include also the treatment in your modeling. And then when you are actually doing the prediction, you predict it for different types of treatment. And then you can take the difference between when it is treated, the estimation when it is treated and estimation when it is not treated, basically the potential outcomes in both the cases, and you can subtract this, which is I showed here, and get the conditional average treatment effect. So this is what is being done here to compute the conditional average treatment effect. So now the single learner is quite good in the sense that it's quite simple model, very easy to implement. You just require one model in there. Then it can also handle treatments which are continuous in nature, which is also quite useful. Also, if the treatment is a really strong predictor of the outcome, it works pretty well. But it also has a few cons. So we know that since we were using a machine learning model, and any well-trained model is regularized. So what happens when you actually regularize a model? So what you do is actually make the model less sensitive to changes in the feature values. For example, if you are performing linear regression, which is a very simple model. Okay, so a linear regression, and you perform regularization on it. So what happens is, when you do regularization, the slope basically becomes lesser in case of when you after regularization. So what is happening is the rate at which now the output will change, the estimation will change, will go down. So it becomes less sensitive. So if, for example, your treatment is not a very strong predictor of your outcome, so in that scenario, you'll see that this rate of change, it also become less sensitive to the treatment itself. So that the thing which we're trying to predict, which was basically the rate of sales with respect to treatment, the price elasticity, that will become smaller, even though in reality it was not so. It was just an artifact created from the regularization process. So this is one of the cons, but still, S-learner is still a good model to easy to implement. It is like if you start out, you can start off with the S-learner and see how it performs. So it will still work, but in case where the treatment is not a very strong predictor, there it might actually lose a lot of information. How can you overcome such a scenario? So you can go to what is known as a T-learner, which is basically practically stands for two learners. So what we do is we take two models instead of one. We take two estimation functions, one which you use it for the treatment to model only the treatment, and another one which you use to model only the control. So once you have the two models, you can then again compute the potential outcomes for both the treatment and the control, take the difference and obtain the conditional average treatment effect. So that basically solves the issue which we saw here, which is basically there is no chance of any regularization happening on the treatment itself in this scenario. Of course, what you lose here is basically the continuous nature of the S-learners, which was there. So you have to, if you really want to now look at multiple doses, then you have to build a lot of T-learners, which is something which I'll show how we do it actually in our case as well. So the T-learner is actually the learner which we use in most of our use cases as well. So it's quite a handy one, and it works quite well. So right now, what we'll go talk about is how we actually use this in our in Marks and Spencer. So I work for the offers team, and I'm particularly working with the loyalty program known as Sparks. So if you have Marks and Spencer account, you're definitely a Sparks member as well. So what is the problem that which we are facing here? So basically, we'd like to provide our customers with the best experience, which also results in a sales uplift for Marks and Spencer. So what is available with us? So we have a dedicated offers team, which basically provide us various offers which we can give out to our loyal customers. And also we have historic data, which provides details on like how did past customers reacted to various offers, which is quite rich as well. We have a few logistical issues. So we have right now the number of past customers is more than 15 million. And in general, like the minimum number of offers we have in a campaign, for example, a clothing on home campaign is around 100. So effectively, you have something like 1.5 billion offer customer combinations from which you need to choose from. So that's a big task in itself. So how we can solve this problem? So part one is finding the right offers. So how do we find the right offers? So we can use the T-learner, which I described before, to actually compute the conditional average treatment effect for each customer offer pair. So basically, we will be constructing since we have 100 offers, we will be constructing T-learners for each of this offer, and then we'll be computing the conditional average treatment effect for each customer offer pair. We also because of some reason because we need to also understand how the redemption looks like. We also create a propensity model as well to understand what are the chances of the customer redeeming a particular offer based on historical data. How do we implement this? So basically we take the data, and then process it on then do our processing, which basically allows us to build a customer offer pair data in a way so that it can be so that we can use it in T-learners. And what we actually do is build several T-learners. For example, if you have 100 offers, you effectively have 100 T-learners, which is then used for predicting our sales uplift. So basically, we look at how much uplift in sales we can get from each individual each individual customer offer pair. So that is what is our that solves the problem of finding the right offer. So that's the part one of the problem. The second part is we need to allocate these offers as well. Now you cannot just blindly, even if you have like very high score here obtained in the first one, it also needs to follow some few business rules. For example, suppose so we have, like, in general we give out something like 3 to 4 offers, and we have a rule, for example, okay, do not give more than 2 women's wear offer to one customer. So because there's certain number of stocks you can there's certain number of stocks you can basically uh, restrict on, and so those things can come into effect. You should also make sure that offers do not overlap. Offers which overlap are not allocated to the same customer, because then it's a sort of a loss for business, because there will be some sort of a double dip there. Now that, for example, jeans, there's an offer on jeans and there's an offer on jeans and jeggings. So technically they are the same offer. One can so they should not be allocated to the same customer. So that's another business rule. And also do not repeat offers. For example, if you got an offer um, for men's jeans in last month, so probably you won't buy a jeans the next month as well. So this is again a business rule which you put in, that we do not repeat our offers from the last month, for example. So these are what we have got here is that, so let's go back, and so we have got the scores, the uplift scores. We have got our business rules, which are the constraints which you need to put in, and we implement this in, again, we use a linear solver to actually solve our problem. So what we have from the previous step is the customer offer array, which gives us the gives us all the uplift values. We have these business constraints which we got here, and then what we use is a linear solver. In this case, we use OR tools. OR tools is actually a suite of multiple solvers. Out specifically, we use SCIP to do the solving. And what it does the allocation based on the scores and the constraints. It will find out the best possible solution of allocating different offers to different customers. So this solves the second part of the problem as to how, in conjunction with how of our offers sales uplift and the constraints, how do we allocate? And this is how we do it here. So what are the impacts here? So we have seen that this has been, so we have started this something more than a year ago, and we have seen that it has doubled the customer participation with higher redemption rates. It has also increased the revenue per customer who redeemed offers. So basically, people who so we are getting more revenue per customer for people who've got these offers. And we have seen an increase in revenue from tens of millions to hundreds of millions, which after we have started implementing these causal models in our in our campaigns. So yeah, so this is where I'd like to end my part of the slide, and I'll hand over to Behzad, who will give a short overview of what we have covered.
Okay, so let's see. Thank you very much, Dipankar. Let me just quickly share my slides. Yeah, thank you very much for your attention. So what did we talk about? We had a brief look at causal inference. We gave an introduction to causal inference. The framework that we use is average treatment effect. We had a look at that as well. Now, to calculate average treatment effect, or in this case, conditional average treatment effect, we use meta-learners. We looked at 2 of the examples which are used in this specific case study. And then we talked a little bit about lessons that we learned and, how it affected us in terms of revenue and in terms of customer engagement and all that. I hope you enjoyed the talk. Just before I go, I want to say that we are recruiting data scientists. If you are interested to work problems such as this one, or usage of causal inference in time series, which is another one that we use a lot, please scan this QR code here or that link there. I put a bit.ly as well, 3RKRA73. You can use that as well. And obviously our contact emails are there as well. Please keep in touch and we look forward to receiving your CVs. Thank you for your attention. I pass it to you, David.
Thank you both very much. Dipankar, we have to get you back as well. This is the proud moment on the stage, actually. So yeah, get both of you on the screen. In terms of the chat, there's already some comments coming in saying thank you, but you know, there's been 240 of you watching along at home or wherever you are in the world. So yeah, if we could have a virtual round of applause, that would be absolutely fantastic. It's always nice when, you know, people give up their time to put together these sessions that they know it's been appreciated and people have enjoyed it at home. So we'll let a few comments come in on the chat. There is already 11 questions in the Q&A, so we'll fire through some of those. But just as we get to those, the chat is exploding, guys. So yeah, it's worth having a little read along at the same time. But I'll do my best to quickly fire through a few. Sally Sam, really well explained. Thank you. Chris, thanks. Ben Keane. Leo Morgan, fantastic talk. Thank you very much. Good to see you here, Leo. Michael Bateman, thanks. Jack Lodge, thanks. Behzad and Dipankar, and thanks for hosting, David. Rohit, fantastic session. Thank you, guys. There's another 30 comments. So yeah, a few regular names. Adam Hornsby, great to see you as ever, Adam. Tom Hudson, Adash, Nima. The list goes on and on. So it's really nice to know that you've been very well received, both of you, from Marks and Spencer's. As Behzad did mention, obviously Marks and Spencer's are hiring. We really appreciate the support of all of our sponsors. Marks and Spencer's are very community minded. They do it to support the community, but equally, if they can hire some people from the partnership, I'm sure that helps the people that sign off the checks next year as well. So please do check out the careers website. I'll queue a few questions now, and then we'll go from there. So the first question at the top there is from Janice. How is this methodology you're talking about, S&T learners, related to uplift modeling? What we do find with some of these questions, sometimes they are answered later on in the session and stuff like that, but it's always, I find, really worth just recapping everything as well. But if we could go to that first question there from Janice. And I don't know, does that land better with one of you than the other, Dipankar or Behzad? Who would like to answer that one?
I can do that.
We're going to have to work on the muting in between so that we don't get that echo.
Okay. So yeah, so basically what we are doing is I'll take the example of T-learner because that's what we are using here. So what we understand is that given an offer.
One second, Dipankar. We are still getting a bit of echo, and I assume it's because you're both so close together, but hopefully we can sort that one out. Technology, man. We love it, don't we?
Are you still getting echo? No?
That's fine now, actually.
Yeah.
Thanks.
Yeah. So basically what we are doing is we are using the T-learners to understand how we to understand the effect on sales. So basically by looking at the difference between the treatment and the control model, you can understand how much incremental sales you can get from this particular from a particular offer. And that's how you get an understanding as to, okay, which offer will affect a customer, will increase our sales from a customer. And that's how you can compute the uplift. Basically, that's the equivalent of the uplift there. Of course, we also scale it by our redemption score to understand, okay, this is the, like what Behzad was talking about, expectations. Our expected uplift will be multiplied. It will be the computed impact, incremental sales multiplied by actually the redemption score, because that would be effectively the best sales values you can get from there. So that's how you get it out in our case. Yeah.
Amazing. Thank you very much, Dipankar. Next question there is from Sally Sam. How long did it take to produce the first version of this model, and with what team size? How do you validate that the model is doing what you think it is doing? So if one of you could perhaps give us a bit of context about the history of the project and the team size, and then a little bit about that validation, please.
yeah, so yeah, so basically this work started around I think it started around end of 2019. It's where this work was done by another member of our team. This was started it, and a lot of the work was done in that part. There were lots of methods which are tried. So definitely T-learner was not the one which we tried. So we went through a lot of different types of meta learners, different types of approaches. Even for our even for the allocation bit as well, there were several approaches which we tried for allocation before we settled onto a linear solver. So it did take some time. So I would say definitely around a year and a half to completely perfect this. It's still, I would say it's still evolving. I'll not say it's perfect. I see one of the questions there, which is actually we are trying to address as well, which is about the independence of the offer. So that's still an issue which is an issue which might affect us as well. So we are still learning. We are still making our models better. But yeah, it does take around, at least I think we were around 2 to 3 people always on working in there. And right now in offers team at least we are about 4 or 5 of us. So yeah.
Amazing. Thank you very much for that context there. I'm sure it never ends, does it? There's always some more improvement to be had. So the next question at the top there is from Adam Hornsby. Adam's got a lot of experience in this area. He works over at dunnhumby. So Adam's question is, congratulations on generating so much uplift with causal models. Can you tell us a bit more about what was the baseline that you were comparing against?
So we were comparing against some of the older, so this campaigns were started, so there were still campaigns that run before, which was not done in a different way, not exactly through data science models. So we already had data from before, like how the campaigns are done. Even we still have a few campaigns which are not done through pure data, like through a machine learning model or T-learner. We just allocate based on business rules. It was compared against those models and seen as so how much uplift. So of course the predicted uplift, and this can vary with time over. But in general, we saw that now that we have data over years, from times where there were only business rules based methods to the one machine learning ones, and of course we had to take into account COVID and everything as well. So I think without that thing removed, I think from there we get that was a baseline basically when we didn't have these models put in. Now this is now if you want to improve our models, we do not base it on the last one. So if you have built a new model, it will be compared against the current one. So it will not be 100 million uplift. I'm pretty sure if you go it in that way. Yeah, but this is from compared to the previous approaches we had from the past.
Amazing. Makes a lot of sense. Thanks, Dipankar. Again, Behzad, jump in at any time. Yeah, I'll keep firing the questions. There's still 23 outstanding. I'm sure we won't get through all of them, but I'll fire through as many as possible. So it does feel a little bit quick fire, but both of you just jump in as you feel most suitable. So based on upvotes, the question at the top there is the question from Tom Hudson. Tom's asking, how do T and S learners address the problem of causation versus correlation? It seems like they're just modeling the effect of a single variable. So can you outline a bit more about how that works, if possible, please?
So we take into account, so the basic idea is that when you are doing such a model, you need to take into account as many features as possible so that you get rid of, so any confounding variables should also be there, and that goes as a part of the model. When you do that, then the effect, so basically you're modeling, so when you do that in using regression or any machine learning model, you are basically subtracting all the effects from any other confounding variables as well. And you are basically left with only the treatment effects effectively. Now, there's a big if there. We have assumed that we have covered all the confounding variables. Now, that might not be the case, of course. But as long we are pretty sure that we have covered most of the variables there, and then looked at the effect. But that may not be true. Of course, that may not be true. If some situation changes, you might need to add some other variables as well. For example, COVID can introduce a different type of effect there, and your sales might go down because of something else, which you are not covering in your current data. So you need to take care of all this stuff.
I can jump in and I can quickly jump in and explain a little bit. So basically, it's the question of you've got the cause, the blue part on the slide, and the magenta part. So what do I need to add into one of these to get the other one, or subtract? So these are various numbers that contribute into this. And this is very active area. So it's on the basis of what confounder we want to consider, right? So what Dipankar is doing, it looks at various confounder that we know about. What we don't know about, we don't know about. So some of those confounder are that we are not aware, we don't know what is the effect of it in between that line. Another related issue to that is, so basically you've got S learner and T learners. These work very well if in this case, but in some cases, for example, when your treatment size is very small, there are other methods that we use. So for example, there is X learner, which considers this sort of situations within the data. You know, some of the data sets are, for example, treatment and control, the size are not the same, how you can remedize that situation. They work much better. But for this case, T learners work fine.
Amazing. Thank you very much. In between the questions, I am going to keep going back to the chat just to fire through a few more comments just in between questions. So maybe 4 or 5. So I'll fire through a few here. Jane Baxter, thank you. David, thanks. Really interesting stuff. Louise Cook, great talk. Thank you. Adnan, many thanks. That was great. Brilliant. Thanks. Thank you, Behzad and Dipankar. Olivia, thank you. Really insightful. So as you can see, both the list goes on and on. Jumping back into the questions, the top question at the top there is from Chris. Chris says, I'm an economist, so I get very excited about talking about prices. And he's asking, how do you consider the customer cross-price elasticities? In order to calculate a causal effect in a standard model, you would also consider your competitors' pricing and offers. How do you consider what your competitors are doing? Is that part of your model, part of your calculations?
I don't think we look at
I don't think so. No, we don't.
Okay.
Yeah.
We'll add that to the roadmap in that case then. So, but you're like, oh my God, more work to be done, more work to be done. So that's cool. Thank you very much for the question, Chris. That might be something that gets covered next year when Marks and Spencer's come back. Next question there from Nick Priestley. Thank you for the question, Nick. Can you delve into the customer offer pairs, please? So can you tell us a bit more about that, Ida? So who would be best for that one?
Well, basically, the question is that we've got a number of offers, say 100 offers, and then we've got a large number of customers, say, for example, 15 million. Now, each one of those offers potentially can go to each one of those 15 million customers, right? So it's a huge number of combinations that you have here. So the question is which one you choose. And as Dipankar explained, it's basically there are two steps. So first, conditional average treatment effect. What is the best number for each one of those offers for each customer? And then after that, the question becomes, in business, there are a set of rules. So you don't give genes to somebody this month and next time and months another offer. So we use that sort of things. But if you look at it, there are so many pairs, how you can automatically thin down and find the suitable pairs. So for that, a solver is used. Basically, from one end, the constraints are coming in. From another end, the data, which in this case is pairs of offer, customer, offer, and values that comes from conditional average treatment effect. So solve this and give us the best offer for every person. So then those are ordered, you can imagine, and top offer.
Sorry, I've done it as well. I was on mute there, man. I nearly got through the whole webinar without doing it. So yeah, thank you very much for answering that one, Behzad. Keeping it coming, as I say, quick fire. We've probably got about 9 or 10 minutes left, so I do think we can get through a few more. The question at the top there from Lorna Brightmore. How do you continue to collect data on offer propensity when your causal model is live? Can you tell us a bit more about that, please?
So the data, I mean, So we basically have to. So what happens is our model is so we allocate offers, run our campaign, and this campaign lasts for these are not always on offers. So this will be a problem if your offers are always on. We run the campaign for 14 days, for example, and then we do our next campaign run. So we get the data for our offer, even getting a propensity out or everything after the campaign has been done, and then we redo our next campaign. So that's how it is done. So the data is collected before. We do not do anything on live models. In fact, we try to avoid anything live because the data might become incomplete. So we try to avoid using anything which is live right now. So
Amazing.
we only do it after the campaign has been campaign is complete.
Perfect. Behzad, anything to add? I muted you there, Behzad. We were getting a little bit of feedback.
That's absolutely fine. So this is, yeah.
Perfect. Cool. In that case, I'll jump in. I probably would also say I would end up breaking your model, because if someone sends me an offer, I can never resist it. So I'd be your perfect customer, to be perfectly honest. Send me anything, I'll buy it. It's all good. It's all good. Keeping going through the questions. Janice has jumped in and asked another question. So thanks for being so engaged. He's asking about randomized tests. So did you have to do randomized tests with your offers in order to be able to apply this causal inference toolkit? So I think that might have been something you touched on early on in the presentation, but again, it'd be good to just recap or cover that one off, please.
Well, generally,
I'm going to have to get. I've muted you, Behzad, so that's my fault.
Right.
There you go. It's perfect.
So, yeah. So no, we sort of don't do that sort of things because of the cost. So randomized control trials, they are very expensive. First of all, they are time consuming. Sometimes it's not possible. So we can imagine if it is a scenario about something related to people's gene, you can never go and change that, right? So the effect of gene on some activities. Some of them, in some cases, some use cases, even it's not probably not moral to do that. So for example, if you're looking at effect of smoking, is not possible to make people smoke in order to create treatment and control sets. So all this theory is created because of that. No, we don't use any sort of random. Do we use any randomized?
So we actually, sometime in between, I think we tried this by the business. I mean, it's difficult. I mean, it's very hard to sell to the business to give out random offers to anyone. So although it might improve our data, but it's not sort of good for business. And pretty sure it's not good for any business. So unless you're doing medicine trial, which is where I don't think you always do randomized control trial for vaccines or something like this, it's very difficult to do this here. So you have to get away with what we have, which is the data which we collected from previous. Yeah. So of course there will be some sort of a selection bias there, because you might giving like, if you look at, okay, what did you buy before? So if you are buying men's offers, you'll tend to get men's offer. So we try to account for that by, for example, choosing so for food, it's easy. We look at the last 3 months so that we do not, give out. We capture your latest trends as well. So that's how we try to counter for any long-term. We do not want to see effects from 2 years ago and stuff like this. So this is some sort of compromise we have to come to there in the next scenario.
Makes a lot of sense. I think, first of all, very modern from Behzad by not forcing people to smoke as part of an experiment, which is good to know. And also, yeah, it makes a lot of sense, because I guess you could potentially offend people if you potentially completely randomized your offers. People like to feel that you're known, don't they? So yeah, it makes lots of sense. Dimitra has asked the question there: how do you identify the minimal set of confounders to adjust for?
So basically, I can have a go and then you do it for. So in some of our work, so for example, work that we are doing to our time series and all that, a large part of it comes from the business. Okay, we do some rudimentally, things such as, for example, looking at correlation and, how various p-values affect that. Apart from that, most of these comes from the business. So it's an old business. It's been around since 1800. So there are people who know everything inside out about scenarios that we work in. So basically we get it from those people mostly. They help us in identifying confounder in a compelling way. I don't know how you know.
Yeah, mostly. I mean, I agree with Behzad. So most of the time, we do have subject matter experts as well who helps us understand all the all the factors which might affect our sales in general. Also, we have seen scenarios where where we didn't add a confounder and it completely gave us a very bad bad uplift. Sort of, we can see that results. So there has been some trial and error as well, but most of the time we get initially we use our subject matter experts to understand what might affect our uplift models, and also prior to doing the modeling itself, we do a lot of data analysis as well what affects sales in the first place. So basically do some correlation studies with and understanding how we can basically model our uplift properly. So those things come into effect.
Amazing. Thank you very much. We've got about 2 minutes left. We do try to keep this between that sort of 1 to 2 slot UK time. I know people will be joining from further afield, but we do try to keep that. There is still lots of questions. I think what I might try and do actually is get hold of all the questions, perhaps share them with Marks and Spencer's, and we can perhaps create some sort of blog post between us to help answer some of these questions. So we'll fire through perhaps 2 more and then we'll go from there. So I'm actually going to jump to the question from Lars. Lars is asking a bit more about how you test and validate your models and results. How do you manage that?
So basically, one of the disadvantage of treatment effects is it's unlike regular predictions. Where you can actually do validation test sets, doesn't work here. Like very hard. So what you try to do is basically look at previous data and try to understand if for suppose I predict an uplift sales, I look for a previous campaign, and then you can do it in that way and do a comparison. And that's one of the ways to go forward. But there are also ways to evaluate the treatment effect itself, whether it is a good treatment effect. We call it that you compute what is known as the cumulative treatment, and what is the cumulative gain of the treatment, and you look at the curve. So then that curve should deviate from a random model as far as possible. Basically, it covers a larger area, and you can get an idea about how good your model is. But it doesn't work in the same way as how it would work for a regular machine learning model. There are no test sets. It doesn't work in that way because it's not the same. Meta learners are a bit different when it comes to machine learning. It's not the same as a single ML model. Yeah.
Makes sense. Anything to add, Behzad? I've done it again to you, mate. I muted you. I'm sorry. I'm a bit too keen with the mute button. That's what it is.
Yeah.
There you go.
So basically, imagine you're looking at something related to, say, Valentine's Day, right? So we can go back, and in my type of things, which is like time series size, we can go back into Valentine's Day before COVID and, pick and test things related to that. So we can do computation like that. So if we want to say we do better, we can use that sort of situation, or go back, for example, to a year before and calculate, see if the new setting, adding new confounder, what is the effect, and compare the final result. Yeah.
Amazing. Thank you very much. Thank you very much. I did say we'd try for 2 more, but we have run out a little bit of time. So I will start to draw things to a close. Just as I'm doing that, shout out to everyone in the chat. So Jerry, Chris, Akshita, Pankaj, Mo, Paul, the list goes on and on. Andrew, David, Cedric, Crystal, Michael, Cedric, Matt Fryer. Yeah, the list goes on and on. So thank you all for joining us. Thank you for being so engaged. Thank you for coming with all the questions. I feel like we could sit here for another hour and keep going, which is a sign of a fantastic talk. So I personally really enjoyed that. So thank you both for giving up your time. I think it's probably been our most popular webinar of the year, actually. I think we had about 240 people join. So you're clearly very popular, both of you. So you need to go back, share that around the office, let everyone know how popular you both are. So yeah, thank you to both of you. I do say at the end of every session, we really appreciate you giving up your time to come and share with the community. We're very aware it's not just the hour here. You've both clearly prepared the session, put a lot of thought into it. So it's really appreciated by the whole community. And I will just wrap up by again mentioning Marks and Spencer's. Really value the partnership. It's been great fun over the last couple of years. Everybody we've met from the organisation's been absolutely awesome. And hopefully people do check you out through that link that you shared and follow up directly. So I hope that helps. I will just quickly come to each of you just to wrap it up if there's anything to add. And then we'll draw things to a close from there. So I'll maybe come to you first. Dipankar, actually, I'll come to you first, and then we'll leave the last word for you, Behzad, if that's okay.
Yeah. Thank you, David, for hosting and giving us the opportunity to present. It was really good. Really like the questions. It challenges us. The more questions are always welcome. Challenging questions are always good for us. Yeah.
As I'm waffling away, I'll give Behzad time to unmute because I've done it again to him one more time. And we'll hand over to you, Behzad, for the last word. So how did you find it today?
Thank you very much for your attention. Questions were wonderful, exactly spot on, and very nice. So we pick up a couple of items to just think about in terms of external data. I'd like to thank you. And finally, as I said, if you are interested to work on these problems or problems similar to that, by all means, please contact us. There is a link on the slides, and hopefully you will apply if you're interested to work for Marks.
Amazing. Well, thank you both very much. To all of you that are still with us at home, we have got the Data Science Festival online next month. Hopefully we'll see you at some of those sessions, but just drawing it to a close. Thank you, Behzad. Thank you, Dipankar, and thank you very much to Marks and Spencer's. We'll see you all soon. Goodbye.